Now we have to derive a relation n equal to n0 1 by 2 raised to the power n, where n equal to t by t 1 by 2. Here n0 is the number of undecayed nuclei at t equal to 0, that is initially, where n is the number of undecayed nuclei at time instant t. And this small n is the ratio of the total time passed, and this t1 by 2 is the half-life time. That means n gives the number of half-life period passed for which we have to find the number of undecayed nuclei. So from the law of the radioactive decay, we have already derived that n equal to n0 e raised to the power minus lambda t, where lambda is the decay constant, and we also stated earlier that this lambda is related with the half-life as ln 2, that is the log with base e divided by half-life, or we can say lambda into half-life period. This will be equal to log 2. Therefore, n equal to n0 into e raised to the power minus lambda. Because n is the ratio of the total time divided by the half-life period, therefore we can write that t equal to n into t1 by 2. So it is into n into t1 by 2. And we have also said that lambda into half-life period is equal to ln 2. This is equal to n0 into e raised to the power minus n into log 2. This is equal to n0 into e raised to the power, and using the property of log, this minus n will become the power of 2, so we can write it as log 2 raised to the power minus n. It is equal to n0. Now again, using the property of log, e of the log with argument will equal to the argument, that is 2 raised to the power minus n, or we can write it as n0 1 by 2 raised to the power n, because 2 raised to the power minus 1 is equal to 1 by 2. Therefore, we have derived the relation n equal to n0 into 1 by 2 raised to the power n, and this is a very simple relation to find the number of undecayed nuclei after passing the n number of the half-life. Let's take one example. The question is, the initial concentration of the radioactive substance is n0. Initial concentration refers the concentration at t equal to 0. So at t equal to 0, the concentration of the sample is n0, and half-life is 10 hours. That means t1 by 2, this is the half-life period. It is given 12 hours. What will be its concentration? That means we have to find the concentration at time t, and this time t is given 36 hours. That means t is equal to 36 hours. So using the relation that t is equal to n into t1 by 2 half-life, we will get the number of half-life, that means t by t1 by 2, that is equal to 36 hours divided by 12 hours. So 3 half-life has passed. And now we have to find the concentration after 36 hours. So we will use a relation which we find earlier, that is n equal to n0 1 by 2 raised to the power n. This implies that n will be equal to n0, initial concentration is also given n0, into 1 by 2 raised to the power n, number of the half-life pass is 3. So the remaining concentration after 3 half-life, that is the 36 hours, will be n0 by 8. This is the answer. Next question is, a radioactive isotope has the half-life of 10 years. How long it will take for the activity to reduce 3.125%? From the law of radioactive decay, we know that activity can be written as A, that is that instant t, will be equal to A0, that is initial activity at time t equal to 0 into e raised to power minus lambda t, where lambda is the decay constant and it can be written as log 2 by half-life. Using this relation, we can write that activity reduced to 3.125. So A is 3.125 when the initial concentration was 100 into e raised to the power minus, and this lambda can be written as ln 2 by t1 by 2. So we can write it as log 2 by t1 by 2 into t. t1 by 2, that is half-life, is given as 10 years. So this relation is 3.125 equal to 100 into e raised to the power minus log 2 by 10 into t. Therefore, we have to find the time t. Now we have to manipulate the expression. This will be 3.125 by 100 and it will be equal to e raised to the power minus log 2 by 10 into t. Or we can also write it as, taking the log on the both sides, it will be log of 3.125 divided by 100. It is equal to log of e raised to the power minus log 2 by 10 into t. So this can be written as log 3.125 by 100, and it is the log of exponential with base e itself. So we can write it as minus log 2 by 10 into t. Now on the left hand side, we can invert the argument. So it will be log of 100 by 3.125 raised to power minus 1. That is equal to minus log 2 by 10 into t. And this minus, which is in power, using the property of log, we can write it as minus log 100 by 3.125 equal to minus log 2 by 10 into t. Here negative will be cancelled from the both sides, so we can write log of, and 100 by 3.125 on solving will give 32, that is equal to log 2 by 10 into t. So this implies that t will be equal to log 32 divided by log 2 into 10. This log 32 can be written as 2 raised to the power 5. So it is log 2 raised to the power 5 by log 2 into 10. And this is the power which can be taken out from the property of log. It will be 5 log 2 by log 2 into 10. This log 2 get cancelled, so effectively the total time taken will be 50 years. This is the answer. Next question is, half-life of uranium against alpha decay is 4.5 into 10 raised to the power 9 years. So T1 by 2, that is the half-life of the uranium, is 4.5 into 10 raised to the power 9 years. To convert this years in seconds, we will have to multiply with 1 year has 365 days, 1 day has 24 hours, and 1 hour has 3600 seconds. So this much of second will be the time half-life of the uranium nucleus. Now we have to calculate the activity or rate of decay of 1 gram sample of the uranium nucleus. Activity or the rate of decay is equal to lambda n, where lambda is the decay constant, and this decay constant lambda is equal to log 2 by half-life, and this log 2 has the value 0.693 by half-life. This is equal to lambda is 0.693 divided by half-life into n, number of the nuclei at the instant. We are given 1 gram sample of uranium, which has atomic number 92 and mass number 238. As per the mole concept, 1 mole of sample will have Avogadro number of the atoms. Here we are given that 1 millimole, that means if we convert this millimole into the moles, so it will be equal to 6 into 10 raised to the power 23 atoms per mole. 1 mole of the uranium is 238 gram, that is mass number into the gram of sample will contain 6 into 10 power 23 atoms of uranium. So 1 gram of sample will contain 6 into 10 power 23 by 238 atoms. Now substituting the values here, 0.693 divided by half-life is 4.5 into 10 raised to the power 9 into 365 into 24 into 3600 multiplied by the number of the nuclei, which is 6 into 10 power 23 by 238. This on solving will give 1.23 into 10 raised to the power 4 per second. This is the activity of the sample.